Now we're going to see the derivation of one-dimensional bar element shape function. So let us consider here it is a like a one-dimensional element and it is a linear element, and let us say it has a nodal number 1 and here it is a nodal number 2. I said that it is a one-dimensional member, so therefore the each and every nodal point having only 1 degree of freedom. So nodal number 1 having 1 degree of freedom. Similarly, nodal number 2 also having a 1 degree of freedom. And now let us give the coordinate values at nodal number 1. So at nodal number 1, let us say the x1 would be the coordinate value. At nodal number 2, let us say x2 would be the nodal number coordinate value. Okay, so this x1, x2 are expressed in the global coordinate system. The same element, now I would like to draw the same element, but now I'm going to express this element in terms of the local coordinate system. So let us try to express that in the local coordinate system. So local coordinate system, the same element we have taken, nodal number 1 and 2, but now I would like to express this into a zeta coordinate system, because after all I said that it is a one-dimensional element, so therefore it has only one coordinate. So at nodal number 1 it has a zeta, and that would be, let us say it is equal to -1, and let us say the nodal number 2, the zeta value would be equal to the +1. So why we are going to specify the -1 to +1? Because always in a local coordinate system, the zeta is varying from the -1 to +1. Okay, so this would be the very useful point to derive the shape function easily. So now I would like to assume that one interpolation function for this one-dimensional element. So let us assume the interpolation function. Interpolation function. So the interpolation function can be say that, let us say the x would be the variable from the nodal number 1 to 2. So means that here we can say it is equal to the x is a variable function. So for variable x can be assumed that it is equal to the, let us say, a naught plus a1 zeta. Okay, so let us say in terms of the zeta, so means that at nodal number 1 the x becomes that x1, and at nodal number 2 x becomes that x2. Now I would like to define the what is the interpolation function at nodal number 1 and at nodal number 2. So let us try to see that at nodal number 1. So at node 1, I would like to write down the interpolation function. So this is called as an assumed interpolation function. This assumed interpolation function must be satisfied throughout the element. So here you can see that a naught, a1 would be the constant, and the zeta is also a variable parameter. So means that nodal number 1, the zeta value is -1. At nodal number 2, the zeta is equal to +1. Means that the variation of the zeta starting from -1 to +1. Uh, this is the meaning of the zeta is equal to -1 to +1. Now I would like to write down that nodal number 1, the interpolation function. The x becomes that it is equal to the x1, and the zeta becomes that it is equal to the -1. So therefore it is possible to write down that x1 can be write as a naught plus a1 into zeta becomes that -1. So therefore it is possible to write down that the x1 can be write as, here it is called a naught and minus of a1. So let us say this would be the equation number 1. And similarly, at node number 2, let us write down the interpolation function. So at node number 2, the x becomes that x2. So the x is becomes that it is equal to the x2, and the zeta value is equal to the +1. So therefore, if you substitute the x value and zeta values in a interpolation function, that is called assumed interpolation function. So in an interpolation function, if you substitute that, therefore it is possible to write as the x2 can be write as it is equal to the a naught plus a1 times of zeta. The zeta becomes the +1. So therefore it is possible to write down x2 is equal to the a naught plus a1. So let us say this as equation number 2. Now, from this equation 1 and 2, now let us try to find out what would be the constant values of a1, a2. So we see here at the Azimuth interpolation function, if we observe that there will be two constant a0, a1. So to derive the or to define the a0 and a1 values, we need two equations. So I have defined that the first equation is node number 1 and second equation is node number 2. So using these two equations, now let us try to find out the what is a a0 and a1. So let us try to see that 1 plus 2, equation 1 and 2. If you do that one, the equation 1 would be the x1 is equal to the a0 minus of a1, and equation 2 is equal to x2 is equal to the a0 plus a1. So if you add this both the equation, it is possible to write as x1 plus x2 is equal to the 2 times of a0, because minus a1 plus a1 get cancelled. So from this one, the a0 can be defined as x1 plus x2 by 2. So this is a constant value of a0. Similarly, let us try to define the what is the a1 values. By using that, let us do that 2 minus of 1. So if you do the 2 minus of 1, so therefore it is possible to define the a1 value. So let us try to see that in a next slide. So here I would like to take that the equation number 2, that is defined as x2 is equal to the a0 and plus a1, and similarly the x1 would be equal to the a0 minus of a1. So these are the two equation, and this is called second equation, this is called first equation. Now I would like to perform the 2 minus of 1. Okay, so if you do that 2 minus of 1, this minus becomes that it is called plus. So therefore it is possible to say that x2, and here this becomes the minus of x2 minus x1 can be defined as this is equal to the minus sign, minus a0 plus a0 get cancelled, and it becomes that 2 times of a1. So from this one, the a1 can be find out that it is equal to x2 minus x1 by 2. So our previous slide I found that the a0 is equal to it is called x1 plus x2 by 2. So now I would like to substitute this in the interpolation function. I have assumed that the interpolation function x is equal to the a0 plus a1 times of zeta. So if I substitute both the constant in the interpolation function, the assumed interpolation function is equal to x, that is equal to the a0 is equal to that is equal to x1 plus x2 by 2 plus x2 minus x1 by 2 times of zeta. Okay, so this would be the equation. So now using the above equation, I need to be write down the x1 terms and x2 terms separately. So let us try to separate the x1 and x2. Okay, so here let us try to separate that x1 and x2. So therefore I can able to write down this into the x1 and plus x2 terms. So let us try down that separate the x1. See, if you see that x1 is present here as well as here. So therefore, if you take common of x1, therefore it is possible to write as 1 minus of zeta by 2 times of x1. Okay, so because here x1 is there 1 and minus of zeta is there and divided by 2 is there. Both of them having been divided by 2. And in the second one, if you separate the x2 terms, therefore it is possible to write as 1 plus zeta by 2. So here, now I would like to call this 1 minus zeta by 2 into as well as 1 plus zeta by 2. So let us call this as a shape function n1, and let us call this as a shape function n2. So therefore, the x can be written as it is equal to the n1 times of x1 plus n2 times of x2. So this is the expression of the variable x that can be varying from the node point 1 to 2. Similarly, now let us try to find out what would be the displacement function. So these are called as it is called the variable x function. So now the variable x function I've defined that in terms of the shape function n1 and n2. So therefore the n1 is equal to the 1 minus zeta by 2, and where n2 is equal to the 1 plus zeta by 2. So these two are called as a shape functions. Shape functions. This is called as a shape functions for one-dimensional bar element. One-dimensional bar